Okay, I'm gonna go ahead and share my screen. So for today, if you already haven't looked at it, and I'm not gonna spend a lot of time going through this, but I just wanted to kind of give you an overview if you haven't looked at it, at what you're doing today or what you're doing when you get up to this point and how it relates to the GP today. So today, you remember how the code that we were doing in the past, we were actually giving the commands, the print beach, the add, the save, and all that. A little bulky and not very realistic. So today you're going to unhard code the machine code. In other words, instead of hard coding in the instructions, we want to be able to take a file, a separate file from the command line, grab that file and use that file for the instructions. And we'll also want to be able to parse that file and do various things with that file. Since we're dealing with these instructions, we're dealing with binaries, and that's why we've been going over the binary and hex to some degree. Jerica, since you're just joining us, just real quick, what I was just saying today, the MVP, you're unhard coding the machine. So instead of just having the hard code with the instruction line by line in that array that we were saving it in yesterday, we're going to rewrite it so that we can actually take an external file in the command line, supply it as an argument for our program, and be able to read that in, parse through it, do to it what we need to do to it. So that's kind of the point of the GP today. And then after you do that, you're going to implement a multiply and print. I'm not even going to, it's pretty simple. And you can read through step 10. If you need to do step 10, then that's obviously going to be a part of it. Step 11 becomes part of tomorrow's MVP. So I hope everyone had a chance to look over the video for today. I'm going to go through this like I did with the numbers yesterday. I'm going to go through this very quickly. Not much of it directly relates to what we're doing today. I'm going to make sure and point out what does directly relate to it. If you have any questions that the video doesn't answer, that I don't answer, that still come up, feel free to ask them. If we got time here, if they're quick, we'll go through them here. If not, we can talk about it in one-on-one, or you can do further research on it. So just to start, did anybody have any questions about binary from yesterday that affected their anything? Okay. So like the video covered, we're used to using Boolean operators like or, and, not, and when we have Booleans, when we're evaluating each side as a true false. But if we're working with numbers, specifically in this, if we're working with binary numbers, zeros and ones, we want to use bitwise operators like that introduction video talked about. So I'm hoping everyone got a chance, like I said, to watch the video. So the main, as the video shows, the main bitwise operators are going to be or, and not. And if you remember, like let's say in JavaScript, if you had something to the if you had something let's see. Can everybody see my screen like this, or do you want me to, is that better with it like that?
No, it's good. It's good. It's good.
It's good the way it was? Okay. Let's just write in a little bit more. So with the and, we'll start with the and actually. So remember like in JavaScript, and I'm just going to kind of pseudocode this out, but if we had if X and Y, and we're just evaluating if X is true and if Y is true. Of course, I'd actually, with the bitwise operator, we're just using the and symbol. We're using zeros and ones. So the truth tables like they talked about, if we have A and we have B, we have 0, 0, 0, 1, and we had 1, 0, 1, 1. Remember, the zeros and ones are like true and false. 1 is like true, 0 is false. The and the or, we're looking for true. So A is false, B is false. Obviously, the output for with an and is going to be a 0, a false. 0 and 1, both of them aren't true, so we have a false. 1 and 0, both of them aren't true, so we have a false, a 0. And then, of course, 1 and 1 on the and table will be a 1. Is that clear for everybody? Okay. Now, if we're doing an or in the truth table, and remember, we're used to seeing the double pipe for an or. Bitwise, it's a simple pipe that we're using. So we don't have A or B, nothing, so that's still a 0. This one's going to be a 1. This one's going to be a 1. This one's going to be a 1 because remember, it's only A or B. So just like when we do an or with the Booleans in JavaScript or in Python or any other language, it doesn't matter that they're both that way. When it reaches that first case, hey, this evaluates out A is a 1, then you get a 1. Is that clear to everybody? Okay. And I know this may be a review. I think they covered this before in the course, but we're just going back over it today because some of it does relate to the project that we're working on. I'm going to jump real quick because the not's easy to cover. There's the XOR. If you remember seeing this one, I think they covered on the video. XOR. And what that's saying is that it's an OR, but it has to be exactly one or the other. In other words, remember how this with an OR will evaluate to a 1, but in this case, because they both are 1, it's not exact, so it's a 0. In this case, true, true, and if just flipped my mouse over, false. Is that clear to everybody?
I just had one question about that. When
Sure.
there's a case for 3, like if there's an A, B, and C, when is XOR like true? Is it when only one of the 3 are true?
So you're saying like if you had just pseudocoding it out, A, XOR B, XOR C?
Yes.
I am 99% sure that in that case, it's only going to be when 1 is true. I don't know that I've specifically looked at that recently, so I don't want to lie about it.
It'd probably be like that the B would have to be different than A and C, I would imagine. Like A and C could be the same, but B would have to be different if it was in the middle.
Yeah, this all gets back into that math logic. That would be a great question if you're interested. There is nothing where that should be coming up on the project. That would be a good question for Beej later on. I'm just not sure the answer on that, and I don't want to spend a lot of time on it, but that is a good question, and I will definitely find out. That would be a good thing to bring to the Q&A later on. And then remember how we had, like, we could say something like that, not X, where we could use that, let's say like back in JavaScript, where we could flip the value around from true to false. We have the same operator here, not, and it is simply the tilde. And keep in mind, all of these operators, the tilde, just like the bang in JavaScript, will sit with no space. If we were doing, X and Y, there's going to be a space in there in C. But same with the or, but with the not, remember, it's going to be right on top of it. So, and then remember the equivalent with that was the bang. The XOR, there is no Boolean equivalent to. And also with the XOR, I forgot to provide that one. So you could say the actual, I was pseudocoding it out, A, and then it is the hat, B. So that's the XOR symbol in the bitwise operator for the exclusive XOR. So we covered the AND, we covered the OR, the exclusive XOR, the NOT, and there's also not AND and not OR. I'm not even going to make a table for those. The simple explanation for those is in the video, and the simple explanation is it's the exact opposite of the AND or the OR, but I guess while it's up here. So if we were evaluating a NAND for this, this would evaluate as a 1, this would evaluate as a 1 because it's not an and this would evaluate as a 0 for NAND. So everyone, because it's saying not and, this is not and, so that's true. Not and, that's true. This is not an and, that's true. This is an and. So not and is false. That makes sense to everybody? And then the last one, the not or. This is false for an or, so it would actually be a 1. This is true for an or, so it would be a 0. True for an or would be a 0. True for an or. So remember, only the exclusive or makes this false. So this is true for an or, so it's false, a 0 for a not or. Any more questions on any of those? Anything? So the real thing that I want to go over today that is pertinent to the project is the shifting that your video, gets a little bit into. So for a bitwise operator, when we're working with, let's say, an 8-bit Boolean, we may want to isolate out an access, and there's different ways of doing so, but a shift is a perfect way of doing it. And there's a couple different uses of a shift. As far as we're concerned, there's not really, like you can use shifts for compressions because say like for a long integer, that's 32 bits, but you could actually store 32 Boolean values in there and just use it as one long int and then move bit by bit by bit by bit by bit between your zeros and ones. But that's a little bit past what we're messing with today. The real reason we're going to do it today, if you haven't gotten to it yet, is that the binary code, the instructions for your computer, for your CPU, the two leading, the significant digits in that binary number. Remember yesterday we had to go in and code how many spaces ahead in memory we needed to jump based on the arguments or based on how many lines that specific command took. Remember that? So the first two significant digits in the code for your program actually contain that information. It will let you know whether there's 1, 2, or 3, just like two binary digits can do. So to be able to access those, we're going to use a shift. So say we had 0 binary 1 1 1 0. The symbol for shift right is simply that. And then this indicates one space. So what we would end up with, remember 0B is just the lead for that's indicating it's a binary number. And to shift it right 1, you now have 0, 1, 1, 1. All this has just shifted over 1 to the right, and this space has been replaced by a 0. If that had been a 2, you would have 0, 0, 1, 1. And this other 1, you can just think of it that it gets pushed off the edge. It goes away. And accordingly, I don't know if there's actually a limit on the integer that you can put in here, because of course a binary, there's only so much space anyways in it, but I believe you could shift as far as you want either direction. So when you're shifting, as far as I know, for today's purpose, you'll be shifting over 6 units, and there's no problem with doing that. If you are shifting left, that same number, it's just the opposite. So if you shift left 1 unit, yeah, 0 binary, 1, 1, 1, 0, and then 0. That's actually, I guess, what I wanted to write. And then if you had the same number, then if you had the same with the 3, like we did above, zero, correct. So does that make sense to everybody? Pretty simple. It's just telling you, your arrows are pointing left and right, which way you're going. And you're just indicating how many units. And we see if everything moving to the left, then we're having to just add zeros in its place. If everything's moving to the right, you're just moving everything over, and then you can actually end up pushing things over the edge like we demonstrated earlier. So the video also briefly covered masking, and I think it gave a pretty good explanation of it, but let's just say if you had unsigned X equals, and we're going to say binary 0, 1, 0, 0, 1, 1, 0, 0. So say we wanted to extract these two numbers right here, the 0 and the 1. So just real briefly with masking, what you can do, obviously we need to get these 3 out of the way. So what would be the easy way to just get these 3 out of the way? Somebody. We need to get
shift.
Shift what way?
Shift to the left, I would say. Well, no, to the right. To the right, sorry.
That's all good. So unsigned Y will simply equal X. We'll shift to the right 3 spots, and then that's just going to give you 0, B, 0, 0, 0, 0. Let's see, did I get that right? 1, 2, 3, 4, 5, 6, 7, 8. All right. And these zeros aren't necessary that I put in there. I just put them in there since we're dealing with 8 bits. But now we've got to this. Now we've got to the 2 digits that we want. And if we just want to be able to isolate those out, so remember the masking, how that works. If we have 0B, 0, 0, 0, 0, 1, 0, 0, 1, how the masking works. And then you could say, and, because remember these bitwise operators operate one at a bit at a time. So what this does, remember like the video covered, is the output would be 0B. And remember, the 0, when we have a 0, when we use an AND for a mask and we provide this other binary, the 0 is going to negate. If there's already a 0 up there, it's still going to be a 0. If there's a 1, because a 1 and a 0 is a 0. 0 and 0, 0, same, same, same. 1 and 0 is a 0. 1 and 0, 0, 0 again is 0. 1 and 0 again is 0. 1 and 1. And now we have that 0, 1 that we were trying to get. But the important thing for today is going to be the ability to shift with these bitwise operators, and that's really all you got to worry about. So anyone want me to do a quick demo of how the shifting will actually work with the code? Yeah, okay.
Yeah.
So hold on. So say we had in our register, remember these first two numbers, 1, 0. This is telling us that we have two arguments, because this is the 1 place, this is the 2 place, and it's just kind of theoretically taking these first two. So this is telling us we have 2 arguments, and then the rest of it can be whatever we want. So 0, 1, and then 2, 3, 4, 5, 6, 7, 8, whatever. So we can make an int add to, we'll call it add to PC. Remember, the PC is just the same as the counter that we were using yesterday going through the memory. So we can say int add to PC equals, and we have our IR that we set up there, we hard coded. We're going to shift over 6 spaces. So remember, it's going to get rid of all this, and all we're going to be left with is the 0, 1. And it'll pad the back end of it with zeros. So then we can say like a switch yeah, and then here you could just say like to do, and then break, like we do, to be in. And then remember the struct that we've got for the CPU, so we can say to this PC plus equals add to PC. Does that make sense to everybody? So every time that it reaches, every time you reach an argument, okay, remember your arguments are these binaries. So your register is holding this argument, this just some number I made up. And we know, or this command, we know that this is the first 2 significant digits are going to tell us how many arguments, and therefore how many places we need to increment up when we're through with this operation. So say this is an operation that takes in one argument, so it needs to skip 2 places. 2 places, excuse me, I said that wrong. So we're creating an int and saying add to PC, and we're simply doing a bitwise shift to the right of 6 places for IR. So what we're left with, what this is leaving us with, is 0, 0, 0, 4, 5, 6, 1, 0, 0, B. It's leaving us with this. 2 in binary. And so then when it goes down to this theoretical switch, it goes to a case, it breaks out of the case. This is just all kind of a place filler to show you it's doing that. And then after it, just like every time when we had, but instead of having to increment up for each one here, having to worry about, okay, well, LDI needs to increment 2 times, and another one needs to increment just 1, and another one needs to increment 3. We simply, in our CPU struct, in the counter, just add this number. Now, yes, you can't just do this with this binary number without converting it over to a decimal, but we talked about converting that. That's part of the project, is being able to do that. And we'll do a little bit of conversion later today when we're dealing with some of the numbers in the rest of the demo. But anybody have any questions about the general way to go about doing this? This is definitely an important part of the project. So do y'all want this code? Or, all right, drop this in the. This is very much non-functional, kind of pseudocode-ish demo, but it gives you a reference. All right. So as far as the and or goes, and the or, the not, the bitwise shifts right and left, the not and, the not or, the exclusive or. Basically just think of them in much the same way that we thought of with the Booleans, but instead we're evaluating zeros and ones. 1 is true, 0 is false, and when we're evaluating them, it's just evaluating them the same way we did with Booleans, but it's how we have to evaluate them when we're dealing with numerals like this. And the point of all that is to be able to do something like we just did here, to be able to access, and you may have many different reasons to access a piece of what these binary numbers that we're using, but the main point is to be able to access these leading 2 significant digits for the amount that we need to increment the PC. So that'll give you a good place to start with that. Anybody have any questions? Any questions on that? All right. The big thing that we're doing today is unhard coding the machine. So like I was talking about, the way it existed yesterday, the final code that we had yesterday, we were hard coding in the machine instructions as a variable in the top and then reading through that. But today we want to be able to parse it from the command line. So that will be kind of the end result of what we're doing today. So some of you maybe a little bit rusty on file IO, so we're going to go through that and just kind of build forward with what we do. If anybody has any questions about the syntax, be sure and ask. I'm going to try to cover any of the syntax that I think is something that's hasn't been commonly used or might not jog your memory real quick. But for starters, we're just going to read in a line from a file. So we can say include standard IOH. We'll have our int main and a void for right now. That will change. So line 5, file is not a reserved word, but what file is allowing you to do that's part of the C system, basically what this is allowing you to do, it's actually this, but like I've talked about in the past when I had y'all, when I did intro to C, if we had multiple arguments, this would only apply to the first argument. And even though it doesn't matter so much in this case, by convention, we're doing this. So all we're saying is we're going to have a variable, FP, that's a pointer, and it's a pointer that's allowing us to access a file. I'm also going to create character, and we're going to make it linked 1024. So this is simply an array, the size 1024, array of characters. And then with this pointer, we're going to say fopen, file open. We've got to give that an argument. So we've got this file here, print8.lsa. Simple file that's just got instructions. And it's got these comments built into it that show what it's doing. So we're going to want to be able to open that. It's sitting on my desktop in the same directory. So we can simply say print8.ls8. And you don't have to have this R right here, but that's just saying all we're going to do is read. By default, if you include nothing, it's read. But if you need to write, if you need to do some of the other things with it, you need to specify it. But just kind of by convention and to make it really clear what we're doing, it's nice to put it in there, but know that you don't actually have to have that in there. You can just have this. Real quick, it's kind of going into more detail than's definitely known for the project, but know that when you open these files and start working with these files, you're not actually, the operating system isn't going to that place in memory and directly reading each time you're asking it to read or writing each time you're asking it to write. There's actually a buffer, and that's why it's so important to close it later on, because it flushes the buffer. But just know that it actually, say you may need to go in and read, 8 bytes or something like that. The operating system may actually go grab a kilobyte, I don't know, in a buffer, and that way it's assuming you're probably going to want to do more than that, and it's much quicker because every time we have to go to memory, even in RAM like we're going to, it still takes time. So you're working in a buffer, but within this file system, at times on its own behind the scenes, it's actually going and then getting more to read, getting more to write, whatever the operation you're doing. So no, it's actually working on a buffer, and it's not working directly on that place in memory. But then in the process, it's working on the place in memory. If you want to learn more about it, read up like buffered versus unbuffered operations, input-output operations in an operating system. But that's a lot of boring detail that doesn't matter here. But it's just a little fact that I wanted to throw in that's outside of what we're doing. So we can say while file gets 3 arguments here. Line, I'm going to say 1024 FP. And we'll say not equal to null. We'll just print. Remember, we have to have a formatter. We're going to have a string here because we're reading in a string. Like I said, later on, we're going to deal with that because we'll be dealing with turning this string into usable numbers. And then at the end, we just say F close. And all this is doing right here, it won't, I don't think it'll crash if we exclude this, but you always need to do this because those buffers we were talking about earlier that it's working with, this flushes all those buffers. And just like memory allocation where we need to allocate and then deallocate memory, it's important by practice to clean up that memory and that space that we're using. So that's why I mentioned up here about why it was working with buffers, so I could explain why, if it hadn't been explained before, why it's important to close the file like it does. Again, out of scope of today or any really type of regular stuff that we do with C, but just an interesting fact to know and a useful fact to know. So if we go in and we run this, what did I name this? And see what our output is. Look back up here. Same thing. So what this file gets is doing is we've opened this file and it's just starting to read through the file. And what this is saying is we're going to save it. This is just this is a buffer. Now remember, I was talking, don't get confused, I was talking about the buffer within the operating system. This is just a reusable variable, sort of a buffer that we're using to be able to go into this file, open this file, read this file, then we're storing it in this character array, okay? What this 1024 is, we can actually do a size of here. We'll do that later on, I think. But for here, I just put 1024. So since this is only 1024 in length, I just set the length here. And then FP is actually where we're reading it from. So we're saving it here. This is where it would terminate, and we're reading from here. So long as that's not equal to null, long as it's reading still, we're going to print the line. So long as the line is not null, we're going to print the line. This is just telling it terminate at 1024, or it terminates at the new line if it reaches a new line. So here, it keeps reaching a new line. And then with the while loop, every time it goes through, it's overriding this little buffer that we made here. Everybody clear on that? Any questions? This is important for today, so if there's questions, ask now and don't get stuck on it later. Clear? All right. I'm going to drop these codes as we go, but we're kind of going to build on what we're doing today. You'd think after 1,000 times of posting code, now remember, this code is dependent on this file You don't have this file. I can drop it. I can compress it and drop it later if you want to play with this stuff. But all this is pretty much serving as a demo. Once again, you just can't cut and paste this into your project, just like yesterday in the metaphor machine that I made. But it's a good, not starter code, but it's a good base to be able to understand how you need to go about tackling your tasks for the day. The next problem that we have here is I'm still hard coding right here where I want to read from. Ideally, we'd like to be able to do this in the command line, right? So some changes that we need to make if we want to do that. First of all, if we're going to accept command line arguments, I'm going to spend a little bit of time talking about this because I want it to be real clear, not only for the project, but just very clear how this works, because it's not confusing, but it's a little complex. And I actually had to go, most of this stuff in C, I just remember I do it a lot. I actually had to go back and look at this just to make sure I had it right, because I know what to do, but I didn't exactly know why. So I wanted to go back and make sure before I went over this. So for here, we're going to say int arg C char pointer arg v. Obviously, you don't see this appearing anywhere else here. This is dealing with the command line, and we'll get into it more later. We're going to create our same variable that we did here and our pointer to the actual file here that we did. The first thing I'm going to do is a check. You don't have to have this, but it will crash if you don't. I can demonstrate that later. This is just kind of a generic error message I'm creating that's saying, hey, look, we need to say what file we're dealing with in the command line, and you need to give a file name for what we're wanting to read from. But this means, just know this means nothing. This is just a placeholder here. And we will return 1. Remember, return 1 is actually return 0. We have this int for a return. This actually means that there was a failure. It's kind of weird because normally 1 is true, 0 is false, but return 1. Return 0 in C is success, return 1 and beyond is a failure. What we're doing here is making sure that there's 2 arguments in the command line. So if we tried to run this and we didn't specify the file that we're going to feed it in the command line later, it's going to throw this error. So all this is saying is if argc, that's just the number of arguments. If argc is not equal to 2, the first argument being the actual file that we're dealing with, and I'm going to demo this later on, so in the command line, so maybe it'll make more sense if it's not in there. But if there's not 2 arguments, then it's going to throw an error. And then we're going to have our same open, but what we're going to replace that with here argv1. So know that argv1, I'm just going to argv at the 0 would actually be arch2.c in the way that I've named it. argv at the 1 is equal to this print8.ls8. So the first argument, the command line argument, is actually what file, this file that we're going to compile and run. The second argument is this file that we're reading in, that we're going to supply it in the command line. So we're just telling it right here, hey, take that second argument, and notice we've got two arguments. That's what this internally is creating. You don't have to do anything else for it. This is just knowing, hey, we've got two arguments here from the command line. Everybody, is that clear to everybody, what I'm saying? So this is simply saying, take what we're trying to open, and we're going to read it. And then we're going to put another check in that says if FP, now that we've opened that file, that equals to null. If that file, if that file doesn't exist, and we're just going to have our string formatter. Have the string formatter here, and then we will call that arg v1. Printf error opening file, string form, new line. And we're just giving it the name of the file here. Once again, we don't have to have this, but this is allowing us to have some error checking in there. And this line will remain the same. And then we exit, we'll close. So all we're basically doing here is setting up the same variables and pointers. We have a check to make sure we have two arguments, and that is making sure that we supplied it. Obviously, the first argument's got to be there for what file we're dealing with. We're making sure that we're telling it what we need to read. If you don't do that, we can't do anything anyways. So then we're just opening it, and we're replacing it with that second argument, this file that we're going to access. And we're just going to make sure that file exists, that it's just not returning a null, that we got something to work with. And then we're using that same fgets and reading each line and printing each line until we get to null, which would be the end here. I think if we run this, if we compile this, we don't get any errors. Well, that was stupid. And you just got a demonstration without me even needing to get a demonstration of why we have that error check in there, because my silly self did not put print8.ls8. And now we get it. So then to show you what else, if we, let's just say we called this print.ls8, we get that error message. And it actually throws a seg fault in there too. Or if we don't include this, let's see, let me save it here. This will crash out. It should crash out. But it's going to let me. And I won't give it a second warning, or a second warning, a second argument. And see, without even giving us an error, it gives us its own error message, but it crashes. But with this in there, we have our own customized error message. There we got it. Anybody have any questions on any of the syntax or what we've done here? How we're able to read in from the command line? So the next problem that we run into is, oh, hey, we're parsing that string, but we need numbers, right? Got to have numbers to deal with. So we got to do something about that. So I'm just going to keep using the same piece of code. There is now another dependency that we need. And we need this because of an operation that I'm going to use here in a second that I will show you. So we're going to get rid of this. And what we're going to do is we're going to say unsigned char. Remember we talked about that yesterday, the unsigned characters. And we're going to use this string to unsigned long. 3 arguments here, line, null, 2. And then we'll say print f 0 to x. And don't worry, I'm going to talk about why we're doing this.
Can you increase your size a little bit?
Sure.
Thank you.
Ah. Better?
Yep.
Cool. And if this works, and I'll explain what we did here. And notice now we have nice hexadecimal numbers. These are actually hexadecimal. These aren't decimal. These are hexadecimal, but I'll explain what we did. So we got all the same code that we just dealt with. But instead of just going through here while we're parsing through this information and grabbing this binary, we say we don't want this in binary. In this case, we want it in hexadecimal. So we use this command, and we're just making an unsigned character like we did yesterday. Remember the unsigned char, it allows you to go between 0 and 255 instead of negative 128 to 127 with an 8-bit binary number. We don't need negatives, so we can go from 0 to 255, 256 digits. And we're just going to call it val. We're using this operation string to unsigned long. It's included in here in the standard library. And we're going to say save it to line, same variable that we were using earlier. This null, what this null does, what this argument does is it says, okay, I'm going to keep reading, I'm going to keep reading, I'm going to keep reading in here until I get to the point where I can't read anymore. And the null is just saying we're not going to worry about it, and I'll show you what it does in the next demo. But what it would do if it terminates while it's in the middle of reading, it'll actually store a pointer to where it terminated to in the file that it's reading. Does that make sense? If it's not able to keep, if the string to long is not able to keep saying, okay, this 1000001, And if there's a problem in that, it'll save that pointer if we want that pointer. And we'll see a reason why you might want to save that in a bit. And then all this is doing is it's telling us that we're reading in a binary number. This is the base. So if we were reading in a base 10, would say base 10. If we were reading in hex, would say hex. In this case, would say 16 for base 16 for hexadecimal. In this case, it just knows we're reading in binary. Everybody understand what the arguments do? Where we're saving it to, the pointer to where it's no longer able to read, which we'll demonstrate here shortly. The end pointer, it's actually a pointer to a pointer. And then we're doing it binary. This print, this format specifier is saying print this. We're grabbing a binary, but this format specifier allows us with the X to say print in hexadecimal. And hence why we got this output that we did. It changed this binary to hexadecimal under the hood. This 02, because remember the hexadecimals we'll be dealing with are only going to be 2 characters long. That's the most they can be. This 2 is just saying make this field width 2. Each of these this field only needs to be width 2. There's no reason for anything else. This 0 means, hey, like right here, for consistency and probably best case to always do, this would actually only output as a 1 because there's nothing here. This would output as an 8 because there's nothing here. So this is just saying, hey, if we don't have anything, pad the empty space with zeros. Does that make sense? Everybody, if I took this out and I saved it, I went back down here, compiled it, then we ran it, see what we end up with. And that may be difficult to deal with if you think about it. If we're dealing with taking these values in and dealing with them later, we want them to be consistent. So we want them to be 2 in length because we're dealing with hex in this case. Let me go back and fix this. I'll drop this code. All right, anybody have any questions on what we did there? Everybody good? And then here we're going to see what this was all about and how we can kind of use that. But change this a little bit. And it's fine like it is. And then in this while loop, I'm going to create a variable pointer. And we're going to call it end pointer. This is actually, if you look in the man file for C, that's the name of this argument. We're going to have our unsigned character, same for this. Remember, this is actually a pointer to a pointer. So we're going to say at the address of end pointer. So we're creating a pointer here, And remember, this is going to return a pointer if we have a problem here. So this is now allowing us to grab this end pointer if we have a problem. And then we'll just put an if statement in. If line equals end pointer. And this is just saying, hey, did we actually have something in this file that we were not able to read in and read in the string and convert it to an unsigned long? Do we have a problem with that? Then what can we do with that? So if we have that, if line equals the end pointer, we will print skipping string, and then that will be the line itself. If you see here, if we go back in, I always do this. It still runs the same. But if we were to go in here, let's just say put some junk in there. We don't even need to recompile this, but we will. We run it again. Notice we still get our output. We just get a neat little error message in there that allows us to show what was skipped. So we know, hey, we got a problem. Because it'll just skip over it if not, and keep on going with that while loop. So just another way of error checking. I know a lot of these things I'm showing are error checking that you can get away with not having, but these things help. You may find them useful in your project. Save this. Anybody have any questions on how we did this here? All we're doing is just creating a variable for that endpointer, this argument that we skipped over and just said null earlier because we didn't use it. But now, hey, if we have a problem, we want to know where that is within this piece of the while loop when we were at that problem that I raised but in there, hey, when we get to that new line, there's nothing to read on this new line. It doesn't have a problem. It reads here, and then it ignores all the rest of this. But then when it moves to the new line, if it has nothing to read into that it can use for that string to long, that's when this comes into play in that segment of the while loop when it hits that line. And it just says skipping, and it tells us the line that we skipped. Anybody have any questions? The syntax makes sense. The logic of this makes sense. So what we're doing today, and to put this all together, I'm not going to go back through and type this all out. Like I said, what you're doing today is you're going to take this and you're going to take how we use the bitwise, the bitwise operators. You're going to take that knowledge. You're going to take the ability to program in, to be able to accept arguments into the command line so that we don't have to hard code our machine instructions. So we'll be able to take something like this, commands that we have, and notice here we didn't, remember how in one we were doing all these defines, but in this data we didn't do it that way. We just straight up used the numbers, but we've got next to it what it all is. We want to be able to take this file, enter a command in the command line to run our program we were working on yesterday. and be able to read it, be able to parse it, be able to use it, and that's going to be your job today. So if we applied this to what we did yesterday, basically everything is the same here. The registers, remember the spaces in memory we talked about, those temporary spaces in memory that we use the same. We're going to make an unsigned char memory, give it 128 here. Then we're going to have the same thing here where we're tracking the current index and the running. We're not implementing what I was talking about earlier, being able to use the bitwise operators to skip over this in the example. But what I'm wanting to show is we've used this, the error check, to make sure that we've got two arguments. We created this buffer here like we had earlier. We're having the ability, like we did in the demo just now, to open this file that we've given it as an argument in the command line, making sure that we have a file, error checking for the file. All this is here. We just used saving it to standard error instead, so we have a log of it. And then our output message, these are just escapes, quotation marks, and we're printing out the file name. And then we're supplying it with the file name. And then we're using the fgets. And for the line, we're just going to say size of line. Like I said, instead of putting in hard coding in, we set, remember up here, the line equal to 128. But instead of saying 128, we can just say size of line and have a little bit more efficiency and be a little bit more semantic. Then we're just creating that end pointer, doing the same thing here. But remember, in this case, we're reading in base 10 because the numbers we're dealing with are base 10. We're not dealing with binaries. So we're just telling it we're reading in base 10. In this case, we're not going to print an error message. We're just going to say continue. But we could print an error message if we want. Closing out the file. Changing this value here. And then remember, all this from yesterday stays the same. This is the exact code we used yesterday. Anybody have any general questions about this and how and you can just see how we kind of took all the code that we worked on back over here and just kind of sat it in on top of the program that we were working with yesterday to be able to do that. So what you end up being able to do, look at everything here real quick. This should then if I say arch 3 and I put in this file beej.meta, and we got the print John, and remember yesterday we were adding the 60 and the 25. So we were saving the 65, saving the 25, and then adding what's in register 3 onto register 2 because we used the plus equals. Remember I said I made a mistake the other day when we were in the QA. where with this add actually gives it the registers, what's saved at register 2, 65, what's saved at register 3, 20. It does a plus equal into register 2, so it's going to save 65 plus 20 into register 2, and then print register 2 in a halt. So you get John and 85. And when we run that, that's what we get. And you get the same thing here. If I didn't give it this because of the, you're going to throw an error. If we give it a file that doesn't exist, then it's going to give us that error message that we coded in above. Can do it right. Anybody have any questions about anything we went over today? Does anybody have any questions about binary from yesterday? Like I said, if you're having trouble with some of the other bitwise stuff, we can get together in one-on-one and talk about it and work through it. But everybody understands how the shifts work, how you can shift over like I demonstrated in that short piece of code and get those first two pieces of the code. You don't even have to worry about the masking. The masking is just part of a demonstration on what you can do with the and. But just remember with all those, some of the symbols are a little bit different, but they're basically working the same that we did with the Booleans, but we're just simply working bit by bit. And we have the ability to shift those bits left and right to be able to access certain bits. And in the case today, we're wanting to access those two leading numbers, the two significant digits, to be able to work with them. And then we saw how we're able to open a file, work with it and close it, how we're able to implement that into opening a file that's in the command line argument. We went over what's going on with that in the int main when we talked about the arguments that are supplied there, the error checking that we did to make sure that we supplied it with a valid file to open, to make sure once we're opening that file that we have something valid in that file to be able to work with. And then being able to error check to make sure that we're not skipping over a line while we're converting everything over. We're taking those strings that we're going to get and turning them into useful data, turning them into that binary. And I showed you how to convert from the binary to the hex as well. We talked about the hex the other day. So does anybody have any questions that relate to that? Or, I kind of laid out in the beginning what you've got to do with your project today, but it's all centers on this. And then that last part 10, you can read and execute that if you need to do some cleaning up in that. We will have one-on-ones between, Beej will have a Q&A between 2 and 3 as usual today. I'll be holding one-on-ones between 3 and 4. We'll have stand-up between 4 and 5. If you need anything at any other time, please message me. Like I said, the help channel's really not applicable at this point because everybody's in build week. So if you need anything, pass the 20-minute rule, post it in our channel, DM me. We can go from there, but just remember, take the time to read your instructions for today to know what you need to do, and take the time to refer back to the specs to know what's going on. And this should be enough starter code or reference code and enough logic behind what's going on with it and an explanation of all the syntax in C, which really is a lot of that explanation is not even included in our kind of rubric for the lecture, but I always like to explain things so that I think it's important to a point to understand not only what we're doing or what we need to use, but why we're doing it, and then, how all those arguments are working. So if you have any questions about those, use the man page in the command line, Google it, shoot me a DM. If you're having any problems, DM me, and enjoy your lunch. If nobody has anything, I'll get this video posted in a bit. You've got all the reference code. I'll zip those files up and post them in case anybody wants them, that print8 and that beach.meta that I was doing, but there's really no reason you should be playing with this code. You need to be working on that LS8. This just gives you something to refer back to. And the two important ones are the first one that I dropped with the bitwise, and then the last two I dropped, the changes I made to yesterday and the final code I made today. The other ones are just simply building up to that point. There weren't any changes as you saw that happened in those. Everybody good?
Good. Thanks.
Hey, no problem. And don't hesitate to reach out, and I will get this stuff posted in a bit, but get back to work, and I will see you later this afternoon, okay?
Thanks. Bye.
Bye.